Okay, so in this screencast, what we're going to be doing is a couple of problems from Chapter 7 pre-class problems. There were a bunch of questions on this one, so I just want to go over it. So we'll start with the first problem. An object with mass 4 kilograms is dropped from the top of a building after 1.6 seconds. How much has its momentum changed? So to think about this one, I'm going to start with using the momentum principle. So just to remind myself, the momentum principle says that the change in the momentum is equal to the net force applied times the change in time. Okay, so in order to use this, I need to think about what is the net force applied. So in this case, let's think about the mass. And what's happening to it is that it's being dropped from a building. So that means there's a force of gravity from the earth on the mass, on the ball or the mass. And it says ignore air resistance, so that's the only thing that's really acting on this. And I know what the force of gravity is equal to. In terms of magnitude, it's equal to mg. So using that then, what I can do to figure out the change in the momentum is I can say, well, let's call down positive because that's the way things are moving. Then I'll say my change in momentum is equal to mg delta t. Okay, and so this will work from whatever your numbers are, but in this case I have some numbers, so let's just finish plugging this in. So my mass here is 4 kilograms. My g is 9.81. Oh, it actually said to assume gravity was 10, so let's assume gravity is 10. And then I know the time that I'm considering is 1.6 seconds. Okay, so if I plug that into my calculator, I find that delta P is equal to 64 kilogram meters seconds squared times seconds. So that's 64 kilogram meters per second, which has the right units. So I feel good about that. Okay, so then the second part of this problem was, if you threw the object down with a velocity of 7 meters per second, would it change your answer to the previous question? So I want to think about what I've done would change if there was some initial velocity. And nothing that I see would change. The F net still remains to be the force due to gravity. Even though I've now thrown it down, all I've changed is the initial velocity and not the change in the velocity. But let's be a little more careful about that. Let's go to the next slide and think more carefully about how that makes sense. Okay, so we still have our force due to gravity as looking like this, and we still know that the momentum principle is true, that the change in the momentum is equal to the F net times the change in time. Okay, so how can it be that if I start by throwing this ball down with some initial velocity, that it doesn't change the momentum? Well, let's start by drawing a velocity versus time graph for here. So in our first situation, we started with 0 velocity, and we threw the ball down. We called down positive. We threw the ball down, and while it moved down, it slowly got faster and faster and faster. So if we were going to draw the position versus time graph for situation 1, it would look something like this. Right? So what changes about situation 2 is that instead of starting with an initial velocity of 0, it starts with some other initial velocity because we threw it downward. So we'll start slightly upward on our axis. But after it leaves our hand, the same thing happens to this ball. So the slope of this line looks exactly the same. If the slope of these two lines look the same, then that tells us the acceleration for both of these situations is the same acceleration. Right? And if the acceleration is the same, that tells us that the F net must be the same. Okay, so that's one way we could think about how it makes sense. But the intuition that something changes is absolutely correct. And the thing that changes here is the final velocity. Okay, so let's expand the momentum principle out a little bit. Let's remind ourselves again, delta P is equal to F net delta T. But delta P really means PF minus PI. Right? And so this can be written as M VF minus VI. So if we think about the two situations at this point, what we see is that in situation 1, the initial velocity was 0. So with the same net force, if you have an initial velocity of 0, what happens is that you get MF equals F net delta T. Right? So we know this number from the last time, so we know that MVF here would be 64 kilogram meters per second squared, or kilogram meters per second. And we could divide by the mass, which I believe was 4, so 64 divided by 4 So 64 divided by 4 gives us a VF of 16 meters per second. Okay, so that's for situation 1 where V naught equals 0. Okay, situation 2 has a V naught equal to 7. So we can still use the same expression, but now instead of having 0, we actually have something to put into there. We know this is still 64 kilogram meters per second. Okay, so what this tells us is if we divide this by the mass, which is 4 meters, we get VF minus 7 meters per second equals 64 divided by 4 is 16 meters per second. But what we find here is that the VF is 16 plus 7 is 23 meters per second. So what we conclude here is that the delta P in this situation doesn't change. It stays 64 kilogram meters per second. But what does change is the final velocity of these two things. Okay? So the difference in the velocities remains the same, but the final velocity changes as a result of throwing the ball downward.